Forced induction. To understand forced induction, you must first understand volumetric efficiency. Volumetric efficiency is the percentage of air that comes into the motor compared to the actual engine size. For example, on a naturally aspirated 5-liter engine, you would expect 5 liters of air to come in, but in reality, it actually displaces closer to 85 to 95% of that. This is due to many limitations, such as heat and restrictions in airflow, like the intake system and valves. And since most naturally aspirated engines suffer from this problem of never reaching perfect volumetric efficiency, forced induction is here to solve that problem. As the name suggests, forced induction means that we are forcing more air into the engine than it would be able to naturally achieve. Through use of a turbo or supercharger, volumetric efficiency numbers can climb even past 100%, which allows more dense air-fuel mixture, effectively increasing power. A turbocharger uses exhaust gases to drive a turbine connected to a compressor that forces air into the engine. It includes a pump shaft with a compressor and turbine, and a wastegate to control exhaust flow. Turbocharger airflow describes the diffuser and volute in turbochargers, which help stabilize and increase air pressure. Air may move through a boost tube or intercooler before entering the engine, and turbo boost pressure refers to the increased air density a turbo provides. The boost threshold is the point where the boost starts. Matching turbine and compressor sizes to engine parameters is critical for optimal turbocharger performance. Incorrect sizing can cause excessive back pressure or inadequate air compression. Turbo lag is the delay in power delivery while the turbo spools up to effective speed. Twin turbos or auxiliary systems like nitrous oxide can minimize lag. Different methods control supercharger pressure, such as wastegates in turbos and fixed configurations in diesel engines. A wastegate controls the turbo's pressure to prevent engine damage by diverting excess exhaust flow. Wastegates can be internal or external, the latter providing better performance for high flow applications. Boost can be adjusted by changing wastegate springs or using boost controllers. Managing pressure on the intake side to prevent turbo surge when the throttle plate closes quickly. Blow-off valves release air into the atmosphere where CBVs recirculate it. These turbochargers adjust turbine geometry for better efficiency and performance across various speeds. VGTs replace wastegates by using adjustable vanes controlled by a computer. Aftercoolers or intercoolers are installed to cool compressed air from the turbo, preventing detonation and improving power. Air-to-air and air-to-water cooling methods are common. Too much pressure difference between the turbine and compressor can cause parasitic load, reducing efficiency. Boost differential must be managed carefully for peak performance. Key parts for a turbocharger include bearings, rotor, a turbine shaft, and compressor and turbine wheels. Bearings can be especially vulnerable to oil contamination. Turbocharger balance is crucial as turbos spin at very high speeds. Turbos are typically balanced during manufacture to ensure durability at high RPM. Lubrication is vital to prevent turbocharger damage from high temperatures. Regular oil changes and synthetic oil can help manage extreme heat. To prolong life, allow the turbo to cool down with light driving after heavy use. Some modern turbos even have features to provide post-shutdown cooling and lubrication. Due to complexity, most turbos are replaced rather than rebuilt. Proper inspection can indicate if a turbo needs replacement, especially if there are signs of physical contact or damage. Common issues include blockages, oil contamination, and foreign object damage. Proper diagnostic steps can prevent unnecessary turbo replacements. Sources of damage can be identified by examining the turbine or compressor wheels. Exhaust failures often damage the turbine, while intake contamination affects the compressor. Failures, though rare, can occur due to excessive boost or improper setup. Investigation focuses on pressure distribution on turbo components. Driven by the crankshaft, these can increase power by up to 50%. Common types include centrifugal and Roots blowers. Positive displacement superchargers deliver a fixed amount of air per rotation, ensuring no lag and immediate torque. They often use wide cog belts to prevent slippage under high boost. Blower lubrication is generally simpler than turbo lubrication because it often uses a separate supply of gear oil and requires minimal maintenance compared to turbos. Pressure relief valves, they handle excess air pressure in supercharger systems, either recirculating it or venting it based on boost levels. High boost systems may use pop-off valves for additional protection. Single scroll designs are cost-effective but less efficient at low and high RPMs. Twin scroll designs separate exhaust pulses for improved efficiency and performance. Types of dynamic superchargers include centrifugal, which are common in the aftermarket, axial flow, and pressure wave. Centrifugal types function similarly to turbos, but they are crankshaft driven. Blower problems include contamination and leaks, which are their primary issues. Proper maintenance and listening for leaks can prevent major issues. Combination supercharger and turbocharger engines are used in high performance applications such as military diesel engines. These optimize power and responsiveness across the RPM range.